Is there hope? So if most programmers are wanting to program in managed languages, we're going to have to consider how we're going to structure the VM so that it can enhance concurrency and parallelism and not get in the way, and so that it's parallel itself so it doesn't become the bottleneck for performance. I don't have a clock on my computer.
Don't worry, Kathryn, I'll stop you.
I just like to pace myself though, so what time is it? 4 o'clock. Okay, good.
Just use a little less power if you go long.
Sorry. All right. So I've said this part. So let's go back now and think about how the VM is running and what it's doing. So yeah, on a single core, you can think about the managed language is running the application for a little while, doing some VM services, running the application, and then running the runtime. So what's in that purple part? And I'm going to use this color scheme for the rest of the talk, so pay attention a little bit. The blue is the application, and the purple is the work you have to do to make sure the application keeps running. Okay, so the blue has profiling in it, has dynamic analysis, what methods are hot, it does the JIT compilation, it does the garbage collection, it does the thread scheduling. So it's all the stuff that it takes to make this program work, but isn't actually the work of the program. All right? And in the single core model, you had to pay for, you had a cost models which said all these services have the cost and they're directly charged to the application. All right?
Does the purple include things like store barriers that are mixed in with the blue?
So if you're doing a write barrier so that you can do a generational collection, the purple should include that, but that's hard to pull out in a measurement, all right? So you could view the application as having little purple lines all the way through it because there's some other costs that are hard to pull out and measure, right? Yes. So,
okay.
So in this view of the world, the purple contains all that stuff, and I've divided it up perfectly. In the real world, you can't measure it that well.
Got it.
Okay? All right, but some parts, like when you stop the world garbage collection, you can say that's definitely VM services and all charged against VM services. All right? So now we want to make the application parallel. So what do? We introduce some threads and locks that don't work very well because they're the only instrument we have, and we divide up the work. And hey, for this particular application, because it's a typical parallel application right now, running Java, then or any other managed language, you have some application threads, but it's not using all your cores, and they take different amounts of time. All right? Because you haven't perfectly divided up your workload, or you have producer-consumer, where these things are actually doing different tasks, and you just have irregular amounts of time taken up by the application. All right? And then the application threads are communicating with each other to get their work done, and that's part of the reason they don't scale. But each thread has a different running time. All right, so one way to do a managed runtime, and this is kind of the stop the world way, is run the application for a little while, stop all the threads at some point, and you have some cost to doing that where these threads aren't running, run the managed runtime, and it's also parallelized, and then restart the application thread. So you can already see, oh, that's not a great idea, right? Because we're wasting all these cycles as we synchronize everything, and we're limited by the longest thread, all right? So runtime waits for the application. So clearly, making the runtime concurrent, both the JIT and the garbage collection and the thread scheduling, where you get to hide some of the managed runtime on this core completely and squish all these lines together because you're no longer having to synchronize all the threads together all the time. All right? That sucks you over and gives you some more efficiencies. All right? So that's adding concurrency. But the runtime is still on the critical path of the application. All right? So that's a problem because now each of these services are becoming more critical to the critical path of the application when you have idle cores. So why aren't you using the idle cores? They have to be powered up because the application's using them occasionally. Why aren't you using the idle cores for your runtime? So ideally, you could take all the managed runtime off the critical path with just a little bit of communication of, for example, profile data, heap snapshots when you're doing a garbage collection, other things. So you reduce the work that has to go into each application thread, and you offload the VM into these cores that aren't doing anything else. All right? So this requires re-engineering the VM in a pretty different way in order to be able to exploit the resources you have and get it off the critical path of the application. All right? And in the worst case, well, not in the worst case, in the best case for the application, you are scalable and concurrent, and you're using all these, you can use all the cores that are at your disposal, although that's idealistic, but maybe we'll get there. And then, so we've added a little bit of overhead to have this flexibility, but you still have to slow down these threads in order to get your VM services work done. All right? So in the previous slide, all these were built on the same kind of workload, and now I'm describing a different kind of workload that actually does utilize all the processors. David?
You haven't mentioned, I'm sure you will, how much the blue things have to stretch when you do the re-engineering to redistribute the purple things.
They don't have to stretch at all.
Okay, I find that quite surprising. But go ahead with your talk.
So the little slices of purple, they have to stretch a little. So, for example, you have to be delivering dynamic profile data somehow, and that's the example I'm going to show, actually, is how to deliver profile data from the application threads to a consumer thread.
I'm thinking, if you do compaction or code substitution, then the code that's running has to be able to deal with objects moving out from it or different versions of code moving out from it. And that can slow down the mutator code.
That's right.
So that's why I said it seems like the blue things might stretch if you get away from your stop the world approach with the purple.
That's right. So there's some overhead to the application, and depending on which services you're changing, the overhead will be more or less, right? And some of that overhead could be similar to the thin purple lines of a write barrier to have thin purple lines of a concurrent collector going on, right?
And the net effect could be worse. Not always, but could.
Though, right? So you have important design and engineering problems to get this right, okay? So to build this kind of system, you've got to have both the runtime and the application to have concurrency and parallelism. So the runtime has to be aware that that's going on and can't treat the application like it's a sequential application anymore. And you have to communicate between the application threads and the virtual machine threads in a way that's more scalable. So right now, cache coherency is not a scalable mechanism for communicating between caches. So some hardware designs are going to have to change in order for us to even build scalable multi-core processors. But actually, the work I'm going to talk about today views the architecture is immutable, which unfortunately for the software people, it often appears that way. but this is one of the issues that I think the hardware community is going to have. Coherency domains where some parts aren't cache coherent, like the cell is one extreme of that, but maybe parts of the memory or regions of the memory are no longer cache coherent, and the VM or the application says, I'll take care of making them coherent. But then you have to have the high-level primitives that make that programmable. You can't make those domains like locks and threads, all right? And then you're going to have to deal with heterogeneity, it looks like, because it looks like the architects are going to be building more, instead of the homogeneous cores we've seen now, because it's not complicated enough for the software to run on right now, they're going to give us heterogeneous cores, and so we're going to have power-hungry cores that are intended to accelerate the critical path or some sequential bottleneck. So you're going to put more resources and power towards those, and then things that aren't on the critical path can go on these lower power cores, and as long as you orchestrate the application right, that should work. All right, is what they're offering at ISCA this year. That was one of the things that in theory should work, but the complicated hardware and software to build that are challenging too. And then we have specialization. We could specially tune the cores. People are looking at that as a solution to concurrency. So you have one core that's really good at graphics, and we've seen the graphics now as a general purpose computing unit, and you use it not just for graphics, but you can use it for other things too. So there's a lot of things that can be happening in the hardware. And so how are you going to take care of it in the software? What's the approach to exploiting all these changes? So each of the major components of the VM are going to have to be more scalable and concurrent. So I'm going to talk today, the rest of the talk today is going to focus on how to make the profiling part. And there are lots of people in the room that have worked on whoops. It's gray. This all is gray on my version. To show you I'm not going to talk about it. And so I'm going to, because I'm running a little bit behind, I'm just going to focus on that top part today. So what does profiling do for you? And this work is work we presented last year at UPSLA. And it's one mechanism that works with today's hardware. All right? And the student who graduated in the fall last year, Jung-Woo Ha, is now at Intel working in the Intel research at Santa Clara. And then this is joint work with Steve, who's in the room, and Matt Arnold, who's not.